Our next speaker is Mr. Peter Chang. He's the co-founder and marketing manager at Skymizer at Taiwan. His current research focus is in AI hardware software co-design and AI system software, including compiler and runtime. Today, he's going to talk about Tiny ONNC, unleash your IoT device intelligent power. Please.
Thank you, Yuan, and thank you, everyone. And I'm Peter from Skymizer, and I'm going to talk about Tiny ONNC. And in IoT device, as the previous speaker mentioned, IoT devices face harsh hardware restriction, especially in memory. In this figure, you can see the for ARM Cortex-M series, there are various IoT devices. Most of them actually are very small devices like Cortex-M0, M3, M4. They only have limited RAM space like 64 kilobyte or 128 kilobyte, and also limited flash memory, only 108 kilobyte or at most perhaps 512 kilobyte flash. For bigger, larger devices like M7 and XPRT 1050 have 600 megahertz CPU, 512 kilobytes RAM. It's still compared with server, PC, or mobile devices, they're relatively small. And how could this happen if we put AI model into these devices? It will shrink the available operators like this. If we put a model into M7 devices, because it has a 512 kilobytes memory, you could put 80 million operation into it. While if you decide to use M4 devices, there is perhaps like 64 kilobytes memory. That is, you only can put 6 million operations into that devices. So what does it mean? It means limiting computing power means losing accuracy. As this figure shows, if you try to shrink your model, try to cut some operators, cut some layers, it means you will lose your accuracy. So it leads to, for AI solution providers, system integrator, they spend much cost not on data scientists, not on how purchasing hardware. Actually, near 40% they spend on software. The software means they need to figure out how to find the proper hardware, how to find the best trade-off strategy to shrink their model to fit the hardware with limited memory, and it costs a lot and lots of trade-offs. So we provide our solution, Tiny ONNC, and I will introduce Tiny ONNC first, and then introduce Tiny ONNC optimization, show how to shrink memory usage without accuracy sacrifice. And then I will show some performance, some experiment results, and finally I will show you how to use Tiny ONNC for your IoT devices. Okay, first introduce to our Tiny ONNC. First, before introduce Tiny ONNC, I have to introduce ONNC. ONNC is an open neural network collection which provided by Skymizer, and it's also an open source project. And it provides a versatile toolkit for AI on-chip system. We support various neural network frameworks like PyTorch, TensorFlow, TVN, even Keras. And we provide the complete tool chain, including compiler, calibrator, and semi-hosting runtime. We also provide rich execution platforms, including precision simulator, behavior simulator, virtual platform, and even FPGAs. And provide through our development environment, SDK, benchmark, test suite. And we bring this solution to IoT devices. So we provide Tiny ONNC, which is an open neural network collection for IoT devices. We support AI frameworks, PyTorch, TensorFlow, Keras, support many neural network libraries like CMSIS-NN, and Andes, libNN in our device, in our supporting list. And also we'll support various microcontroller, which is all Cortex-M device which support CMSIS-NN. We support this device too. So how everyone, I think you have a basic idea about our Tiny ONNC. So let's dig into it. How we could optimize this solution without performance sacrifice, because we have deep understanding about SoC behavior. According to our observation, nearly 95% execution of when you're executing AI model. Actually, 95% execution time are in data traffic among processing elements and memory storage. And furthermore, when we really analyze it, we will figure out 95%, in this 95%, most of them are unessential data movement, because the bad data location, the bad data algorithm, it leads to unessential data movement and unessential execution. So we optimize the data movement, we optimize data location, which leads to 4.8 times speed up. When we use the YOLO V5 as an example, we just shrink this unessential data movement and unessential data execution. You can see this how software optimization could lead to 4.8 times speed up. And we use our interference graph to figure out which memory could be split, which data traffic could be saved, and we use fire and forget survey to optimize the interrupted mechanism between deep learning accelerator and CPU. Also, not only for model, we also optimize sample data. About quantization, we provide the ONNC calibrator to ensure precision by hardware architecture aware algorithms, which means when you receive a model, usually it uses floating point 32 data representation, but most of deep learning accelerator or hardware, they use integer 8 to execute this model. So how to ensure precision and make sure its performance is still good, the accuracy still good is quite important. And we provide our calibrator to use the hardware support in the deep learning accelerator precisely to ensure their cosine similarity and ensure its performance and ensure its precision. And finally, and most important one is how to save our memory. It's important for IoT devices because SRAM size dominates power, performance, and area. Nearly 60% to 90% area of an IoT chip is SRAM. So this is why that is really important. And ONNC provide two major optimizers to reduce the size of memory. The first one, keep memory temporary and spatial locality of activations that save 46% memory consumption. And second one is we separate large tensors into small pieces to reduce both CBUF and SRAM demand. And as you can see, we analyze what there are weight 1, weight 2, and weight 3. The weight 2 for the weight 2, we have to allocate a large memory space for a time period. But when we really dig into it, we found there is a false data dependency, which means we could split this W2 into small pieces So we could highly reduce memory consumption at the same time, while some may argue that when you split the memory usage, it may take much time, but actually not, because as I mentioned in these slides, most of time spent on data movement. So when we reduce unessential data movement, only leave time for essential data movement, it could reduce large time. So although it seems like it will took much time, but actually no, because we reduce more time on unessential data movement. So it leads to our experiment results. We use Nuvoton M487 as our board, and we use MLPerf Tiny as our benchmark. Of course, you could use our solution to every IoT board which supports ARM CMSIS-NN. And let's take a look about performance and benchmark. ONNC shrink memory and flash usage about 1/2 SRAM and 1/8 flash. We only use 1/2 SRAM and 1/8 flash consumption compared with TensorFlow Lite for micro. Why? Because ONNC static memory planner analyze the liveness of each tensor in interference graph and reuse most of memory space. So as you can see, we use less SRAM, we use less flash, and we speed up. Actually, we speed up at the same time because we reduce unessential data movement. We use memory in more wisely perspective. Okay. So you may have a basic idea about Tiny ONNC and its optimization and its performance. And perhaps you will think, oh, okay, perhaps I want to try Tiny ONNC. How can I do that? Let me introduce it for you. Okay, here's a workflow for deep learning model deployment. For most of people, you're familiar with IoT devices and your host machine for compilation, cross-compilation. But we add our service as compiler source. So how it works. First step, you will get your training model. Perhaps it's the most familiar part for you because you could download it from ONNX model rule, tinyML perf model rule, and TensorFlow model rule. And perhaps you have your own model. Of course, you still could upload it through just in the format of ONNX or TensorFlow. And second, compile with ONNC bench and register your account on Tiny ONNC service page like this app.onc.skymizer.com register, and then get your API key in the profile page over here, and you can have your API key over here, and then you can start to write your Python script to compile your model through ONNC service. The first is login. You use the login function and key in your API key over here. Okay, and then create a project object to create a project, and then add your model and its calibration samples. Here, you could use this function project.add_model to add your model and your calibration samples. We support various models here, including Keras, TensorFlow, PyTorch, or other serialized formats, including H5, PB file, and ONNX file. And also, we support various calibration samples data format, including NumPy or PB file.
So, Mr. Chang, before you move on, we have a quick question from the audience. So, one attendee asks that, was there a component in ONNC that ensures no overuse of flash region to prolong lifespan? Do you have any consideration on that?
Okay, about memory usage, we could shrink memory usage, but for dedicated hardware, perhaps like because it still have its limitations. So if you use like a 64 kilobyte SRAM, perhaps for some model it's okay, but for like Euro V5, it's very hard to put Euro V5 into a 6 kilobyte SRAM devices. So we will try our best to shrink a model to its limitation. And if there's still some gap between your device and your our shrink model, you could then try to remove remove operation, remove layers for your purpose. But we ensure precision, and we try our best to shrink the model. And then you have better foundation to optimize it for your devices.
So yeah, if I understand correctly, you look like you're trying to optimize the size of the flash memory, but you actually don't consider the memory space of the flash memory, right? Current focus is to reduce the size of the memory footprint, not like considering the lifetime of the flash.
Oh, sorry. Perhaps I misunderstand the question. Sorry about that. We optimize SRAM and the flash at the same time. We optimize these two at the same time. Mm-hmm. So we could optimize the memory footprint in SRAM, and also we could reduce flash. Perhaps let me dig into about flash more deeper. We optimize flash because we use different approach compared with TensorFlow Lite for micro. We are compiler based, which means we compile model to executable code offline. So you don't need to maintain an interpreter in your IoT devices. While TensorFlow Lite for micro, they use interpreter based in their code generation. So you need to put a piece of code in your IoT devices for interpretation in runtime. So we just use different approach to reduce the necessity of the code side, the interpreter. So you can see about flash usage, we only use around like 1/5 or even 1/8 memory flash usage compared with TensorFlow Lite for micro.
Okay, thank you.
You're welcome. And any other questions?
I think you can move on now.
Okay, so far so good. Thank you. Okay. So let's back to here, add model, add your calibration samples, and then compile on our SaaS service. So because we provide Python API, so you don't think too much about how to connect a SaaS service. All you need to do is just use a project.compile and decide what kind of a device you use, like heat list. You use perhaps CMSIS-NN library, so you can use device equals to CMSIS-NN, and we will generate the compiled model in the best situation. We use the minimal usage of RAM and the SRAM and minimal usage of flash. So we will you can print response report to see how the RAM usage and how the room usage it is. And then you could use project.save to get the compiled model from the cloud to download it to your client through the project.save this command. And you can see use your command line to see the output. Our compiled model is CPP file and H file. And your input will be .h file, like your input will be models and output will be C and C++ library. and you could compile this CPP file through your IoT devices compilation environment. Like for ARM environment, you may use embed to compile it to binary file. And you could use this binary file on your devices through like the menu of your IoT devices set. And run inference, you could put your input through your sensors to your devices, and boom, you can get the inference result of it. And I think that's my presentation today. And tinyONNC, we are asking for free trial, so please feel free to access through app.onc.skymizer.com/register. And I hope you enjoy tinyONNC. Thank you.
All right. Thank you for your presentation. Do you have any questions? So I have a quick question. So if I see your slides, you develop ONNC first, right? And then you move to Tiny ONNC. Can you actually tell us what's the kind of main different optimizations from the ONNC to Tiny ONNC?
Okay, the ONNC actually basically focus on its target audience is IC design houses. So the difference between ONNC and Tiny ONNC is a hardware software co-design solution. We will connect to, will cooperate with the IC design house at the very first beginning. We will suggest like this, we will provide simulator, emulator, virtual platform for in-house IC design house to tell them what you can put register or SRAM in which part in your SoC. It could optimize for Euro V5. But for Tiny ONNC, our target audience is different. Our target audience is embedded system engineer, or like solution engineer in solution provider, system integrator, or machine learning homebrew developer. They could use this for more popular devices which they can buy. So I think there's a big difference between Tiny ONNC and ONNC.
Okay. So one more question. What's the biggest differentiator compared to the other compiler? There are many other compiler solutions like doing quantization in the middle. So do you actually comment on that?
Yeah, there are many other solutions, but I think for like, if we compare our solution to other solutions, we more focus on inference side. Like, let's say TVM, they have training side and inference side, but you need to use a total solution. Perhaps you need to train on TVM and use its inference. But we support, as I said, we support TVM as our front end. So you can train on TVM and use our inference if you more focus on like memory usage. So a difference between like TVM and a solution is they are total solution, including training and inference. We're more focused on inference, and we're more focused on like memory optimization. And compared with TensorFlow, just like I just mentioned, TensorFlow, they are interpreter based and we are compilation based, which means for TensorFlow, you need to maintain an interpreter in your IoT device, and it costs your flash memory. And while we are compiler based, so we don't need an interpreter in your IoT device. We generate your model. We generate a binary from your model offline, so you don't need an interpreter on your device. I think that's the difference.
Yep, sounds good. Thank you for your presentation again.
We especially want to give thanks to our strategic partners, which really helped us that we can make that event possible. So we have first our executive sponsors. We have ARM, which is the software and hardware foundation for tinyML. Then Edge Impulse, tinyML for all developers. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, end-to-end deep learning solutions for tinyML and Edge AI. And our platinum sponsors, Reality AI. They add advanced sensing to your product with Edge AI, tinyML. Then also we have Renesas, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, enabling edge intelligence. Seed Studio, the IoT hardware enabler. SenseML builds smart IoT sensor devices from data. SynSense, building sensing and inference hardware for ultra-low power embedded mobile and edge devices. And our silver sponsors, we have Aeon Devices, Deep Light, EMSA, Green Waves, Gravity Inc., HOTG, Imagibot, Geekzo, Rixon Technology, and SAP. So we really want to thank all of our strategic sponsors who help us. And I hope you all enjoyed it and that we see you again tomorrow. Good evening, everyone.